Okay, it thinks it's recording. Let's see how this goes, shall we? All right, so. Let's throw some light on the situation. Sorry, Mark, you can't see the screen. That's okay. It won't be too necessary at this moment. Drive and ambition. And courses. And what class is this? Starting to 311. And 2016 spring. And share it with students.
That's
and
us.
yes. And ISM and star formation.
Yay.
Yes. And slide showing evolutionary tracks.
And
Why, here we go. For those following at home, this is slide number 39. There it is in all its glorious glory. Yes, I'm making a video, I think, with my iPad, which I've never tried before since I haven't borrowed anything since Mark isn't here. Hi, Mark. Everyone say hi, Mark.
Hi, Mark.
Hi, Mark.
also, during the video that you recorded for me, I did laugh when you all were trying to find that job.
Oh, good.
You
Did you know where? Excellent. All right, nice.
Why did he put it down, it's rolling. How can you not see that?
Yeah, well, yeah. Turns out that's easy to see when you're watching the video after the fact. Yes. Well, what can we say? All righty then. So, protostellar evolutionary tracks of various masses. Notice that the ones high up there for high mass stars, they're pretty much horizontal. For low mass stars, the 0.5 solar mass star is nearly vertical. And for the solar mass star, it's vertical for a while, and then it does the dipsy doodle. It kind of goes woo-yoo. And so we're going to talk about why it goes woo-yoo. Yes, and then notice that the 15 solar mass star forms in about 60,000 years. The 9 solar mass star about 150,000 years. The 3 solar mass star about 3 million years. The solar mass star about 30 million years. The half solar mass star about 150 million years. Anybody seeing a trend here?
Nope.
Nope. Okay. Well, then let me point it out to you. Higher mass stars form faster, stronger gravity and all that. So higher mass stars do everything faster. They collapse to from protostar to full-fledged star faster. Then they live their lives faster. So it's all about, you know, they're flashes in the pan. Live fast, die young, burn brightly, all that kind of good stuff. So let's talk about some details in all of this here. So erase. Three main sequence evolution. So first thing, once the protostar becomes optically thick, the rise in temperature produces a rise in pressure, and the collapse achieves a quasi-equilibrium configuration. We talked about that once it's no longer transparent, it's no longer free-falling, it's no longer doing the homologous collapse thing. So it never actually does make it down to a point all at the same time. Protostars do not collapse directly into black holes, in other words. Instead, they slow down when they become optically thick, and then the collapse starts proceeding on the Kelvin-Helmholtz timescale. And I'm trying to remember, did I ever have you guys do the problem where you estimate, like, how long would the sun last if it were shining only via gravitational radiation, right? And we found out what's that?
That sounds familiar.
Yeah, and we found, so basically you say, remember you say assume that the sun started out at some very big radius, collapsed down to its present radius, how much gravitational potential energy would it have released? Virial theorem says half that goes into radiation, although if you're just making a back-of-the-envelope calculation, that's not too important. Divide the total amount of gravitational potential energy the sun released by its luminosity, and that would tell you how long the sun could shine steadily at its current brightness if it were as a result of gravitational contraction. Answer around 10 million years. Well, that means that that can't be what powers the sun long term because of the fact that the sun's a lot older than that. But protostars are in fact powered via gravitational contraction. Main sequence stars are powered via nuclear fusion, but protostars, once they reach quasi-equilibrium, their luminosity comes from gravitational contraction. So there is a time period when the Kelvin-Helmholtz mechanism is the source of the star's energy. That's the bottom line here.
Is that just because it's not hot?
It's not hot enough in the core yet for nuclear fusion, and so it's gravitational contraction that's providing the energy at that part. In fact, notice that on some level it's doing a better job than nuclear fusion because the star is much more luminous as a protostar than it is as a main sequence star. The sun, when it was a protostar, was about as luminous as it will someday be when it is a red giant, as a matter of fact. So it was a lot more luminous back then. Does that mean you would see it brilliantly shining in the sky? Well, yeah, that, but when the sun was a protostar, it wouldn't look very bright from the outside, at least at optical wavelengths, because it was shrouded in a cocoon of
Yes.
and more importantly, dust, right, the dust, which means that it was bright in the infrared, but not visible. Yes. So, once protostar becomes optically thick, rise in T causes rise in pressure P. Collapse achieves quasi-equilibrium. And now is governed by the Kelvin-Helmholtz timescale. And notice that the timescale we're talking about for the sun to reach the main sequence, around 30 million years, is order of magnitude what we got for the Kelvin-Helmholtz timescale from how long could the sun shine with its current luminosity, but you know, it wouldn't shine with its current luminosity the whole time, etc. So. Gravitational contraction is the source of its luminosity. So Kelvin and Helmholtz were totally off. As TEF increases, and note when we talk about TEF, that's the effective temperature, that's the surface temperature. And if you got the notes up, you'll just read the notes to say this, but if you didn't read the notes yet, don't. What's the surface, right, for the sun? The surface is the level where the optical depth is, roughly speaking,
2/3.
2/3, right? So that's what we mean by the surface here, the tau equals 2/3 level. TEF is sigma t to the fourth, 4 pi r squared sigma TEF to the fourth is the luminosity, and r is essentially the radius of the sphere that has tau equals 2/3 at its location. As TEF increases, TEF equals T of the tau equals 2/3 level, the opacity of the outer layers becomes dominated by the H- ion due to electrons liberated by metals. Remember, metals are easily ionized, and the sun's continuum opacity is dominated by H-, because remember, H- is hydrogens with an extra electron that's loosely bound, and it's there because metals easily, my eye itches. Man, I cannot continue, just all of a sudden, the corner of my eye is very itchy.
Video discussion.
Yeah.
Why are you watching a video of him talking during?
You'll see during the break.
Yeah, you'll see. Yeah. I want to see if this is still recording. It claims to be, yes, look at that.
Just ask Mark if he's still watching.
Mark, you still watching? DH. Oh yeah, sounds like it's really good. All right, so what was I talking about? Tau equals 2/3 level. Yeah, H- dominates because remember that extra electron's loosely bound. Anything from this like infrared wavelength of like 1600 nanometers and shorter can ionize it. So the sun and stars similar are dominated by H- in terms of the opacity in their atmospheres. Opacity of outer layers becomes dominated by H- ion. Due to electrons liberated by metals. Where, of course, to an astronomer, if it ain't hydrogen and ain't helium, it's a metal. As a result, the envelope, the outer layers become convective. Because it becomes difficult to transport radiation. Radiative diffusion is not as effective, not as efficient as convection when the opacity becomes this high. So the envelope becomes convective. And indeed, often the entire protostar becomes convective. And in 1961, I forget what the C stands for, but C. Hayashi showed that a fully convective protostar moves along a nearly vertical track in the HR diagram. Called the, what would you guess this track might be called? Why could it be the Hayashi track? As a matter of fact, yeah, called the Hayashi track. And that's what's happening at the far right on those evolutionary tracks there. You're seeing these protostars that are fully convective moving down the Hayashi track. After they take a turn, they have to get hot enough for H- to start dominating the outer layers, and then they start moving along the Hayashi track. And essentially, note that when the star later on becomes a red giant, it climbs the Hayashi track. In other words, red giants are nearly fully convective. And so later on, the sun will kind of have a repeat performance where it climbs the Hayashi track, but as a protostar, it descended the Hayashi track. contour, that's right, yes. Okay, any questions? Because I'm about to erase all this. Everybody happy? I'm gonna do it. I'm gonna do it. Here it goes.
Do it.
So let's look at a one solar mass star. Let's very qualitatively draw its track. So here's the ZAMS, not to be confused with GAMS. What's ZAMS again?
Zero H main sequence.
Zero H main sequence, right? So when it hits the zero H main sequence, it's a newborn, cute little gigantic baby star. So note qualitatively that the track kind of does that. Kind of goes wee down the Hayashi track and then whoop, turns up for a while, whoop, turns back down again and settles onto the main sequence. And there's a figure in your book that has certain points labeled, and the ones we'll be most interested are the ones that in your book are labeled 2, 3, and 5. So I'm skipping some obviously here. And point 2 is 1 million years after the start of collapse. Point 5 is 9 million years after the start of collapse, according to a computer model that the figure that is from your book is based on. And point 5 is 25 million years from the start of collapse. So let's talk about these interesting points along the way. Point 2, protostars fully convective during the first million years of collapse. Start to get nuclear fusion at point 2, it's deuterium burning. Deuterium burning begins due to the large cross section. Deuterium is really readily fusible. Said deuterium is stellar baby food because it's the first nuclear fuel that the star burns, but is there a lot of deuterium available? No, so it doesn't last very long. Low abundance limits epsilon, the energy generation rate. Remember, that's the energy generation rate per kilogram that we talked about long, long ago. So collapse is merely slow delay. Now, a planet is something that doesn't have a mass to ever burn deuterium. What do you remember, what do you call something which has enough mass to burn deuterium, but it doesn't have enough mass for the core to reach 10 million Kelvin and start the full proton-proton chain? So if you're in between a planet and a star, you're a
Failed stars?
Well, you're a failed star.
Brown dwarf?
You're a brown dwarf.
Oh,
Brown
okay.
dwarf is the magic word here. brown dwarf, if you're between about 13 and 80 Jupiter masses, you got enough mass to burn deuterium for a while until you run out of it, but not enough mass to ever undergo the full proton-proton chain and become a main sequence star. So brown dwarfs are in a twilight zone between planets and stars, if you will. But there's probably quite a lot of them out there. Point 3, where it takes the turn there. Increasing central temperature causes decreasing core opacity. Remember that Cramer's law says that the mean opacity is proportional to rho times the temperature to the power of minus your number.
3.5?
3.5. 7/10. Yep, minus 3.5. So as the temperature increases, the core opacity is decreasing. Cramer's law says that. And that means the core turns radiative because the opacities drop down. So radiative diffusion becomes more efficient. So it becomes radiative rather than convective. So that means energy escapes from it into the envelope more readily. That says the luminosity rises. But the star is still collapsing, it's still shrinking. So if L is going up and the star is getting smaller, it has to be that the surface temperature is rising, right? Because 4 pi r squared sigma t to the 4th is the luminosity. So if the R is going down and L is going up, T better go up to compensate for the decrease in R. So in other words, we're going to get a leftward and upward turn. So that's why at point 3, we start going left and up. In other words, on the HR diagram. And it turns out that right about the same time is when nuclear reactions begin in earnest. We're still not on the main sequence yet because we still haven't started the full sequence of nuclear reactions. We get the first 2 steps of the PP1 chain. cycle up to the production of nitrogen-14. So bonus, if you remember, what are those first two steps of the PP1 chain? First is proton plus proton becomes deuterium, right? Because one of the protons turns into a neutron and spits out a positron and a neutrino in the process. And then the next step in the PP1 chain is that deuterium smacks into a what and becomes a what?
Proton.
Proton
Helium-3.
to become helium-3. So we start generating helium-3, but we're not quite hot enough yet for helium-3s to fuse to make helium-4, because the helium-3s have 2 protons, makes it harder for them to overcome their electrical repulsion for one another. But we do get the first 2 steps of the PP1 chain. It starts practicing, basically, for when it becomes fully fledged. Due to strong CNO cycle T dependence, the core becomes convective again. So after a bit, the core becomes convective. The stuff under point 2. Leave the point 3 stuff for now. Point 5. So at this point, the nuclear energy generation rate becomes large enough that it makes the core expand. And if the core is expanding, then that means that it's doing work, you're doing work against gravity. So epsilon sub gravity becomes negative because you're expanding the core. So that means that you have to put in energy to do that. So epsilon for the nuclear energy generation rate increases. That makes epsilon gravity negative because the core is expanding. And in fact, the luminosity of the star drops because even though you're generating more energy by nuclear reactions, you're actually using so much of that to expand the core that it reduces the luminosity overall. Epsilon nuclear becomes so large the core expands. So we're, in the royal sense, the royal we, are doing work against gravity. Energy generation rate due to gravitational collapse actually goes negative because it's not collapsing, the core is expanding. Epsilon gravity becomes negative, negatory. So the luminosity actually drops. Decreasing towards the main sequence value. So in other words, 5 is where we begin that final descent, coming in for a landing. Are we cleared for a landing on Zans? Yes, we are. Straight down, that's right, yes. Well, it turns on retro rockets right before it hits. And it's a nice gentle touchdown. But it does, I mean, for a while, it was dust everywhere at that point, but. All right, so. When the core carbon-12 is exhausted, no more of that, well, not so much of that pesky CNO cycle anymore. The full PP1 chain takes over. Star settles onto Zans. And it's like a movie. A star is born. Aw, the sun was so cute. It was a brand new movie he made since we started. And I erased the 0.3 stuff. So that's for one solar mass star, that's the sun being born. How about that half solar mass star? Notice it doesn't have the kink at 0.3 where it climbs back up and then lands back down again. It's always decreasing in luminosity. There's no point at which the luminosity rises because the core becomes more transparent, and so extra energy starts getting out to the exterior. That doesn't happen for the 0.5 solar mass star, so let's talk a little bit about that. For the half solar mass star, carbon-12 is never burned in the core because it never gets hot enough. The sun gets something like 10% of its energy from the CNO cycle. A half solar mass star doesn't get any of its energy from the CNO cycle. It's not hot enough. And for this star, temperatures stay cool enough, and thus the opacity stays high enough that the star stays fully convective, so it's always on the Hayashi track pretty much, so it follows it all the way down to the main sequence. Temperatures stay cool enough. And thus opacity high enough that the star stays fully convective and thus on the Hayashi track all the way down. So it doesn't have that kink at 0.3. There's no 0.3 for that star. High mass stars, we have to say, well, what's with the horizontal tracks? Why do they turn horizontal and just kind of scoot over to the main sequence? And notice that when they leave the main sequence, as we said before, they also kind of do a repeat performance. They move horizontally on the HR diagram very nearly after they leave the main sequence. So it's interesting that it's not a perfect retrace, but there is, somewhat partial retracing of paths when both when stars are protostars, before the main sequence and after the main sequence. High mass stars. In this case, the core temperature rises much more rapidly, and so you get carbon-12 burning and the first two steps of the PP1 chain early on, and that makes them leave the Hayashi track because their cores no longer are convective, they're not fully convective anymore. So off the Hayashi track they come pretty high up, and then they move horizontally after that. Central T. Quickly gets high enough that carbon-12 burning and conversion of hydrogen to helium-3, those first two steps of PP1, begin while star is high up on the Hayashi track. Star leaves it and follows a nearly horizontal track. Pretty much keep constant luminosity as they collapse towards the main sequence. So unlike a low mass star, where it's actually reducing more energy as a protostar per unit time from gravitational contraction than it does when it's a main sequence star burning hydrogen in the core, these guys keep nearly constant luminosity until they switch from gravitational collapse to nuclear energy generation of the main sequence. And, excuse me, any questions? Because that's the end of our coverage of protostars and all that kind of good stuff. And now we're going to move on to the Milky Way and to galaxies. So we're going to treat chapters 24 and 25 together. So we'll talk about both the Milky Way and galaxies in general together rather than exclusively talking about the Milky Way and then exclusively going on to other galaxies. Okay? And as is their tradition, why we'll begin. What's that?
Crash course?
Huh?
Crash course?
Crash course, that's right, crash course, yes, that's what I was gonna say. I just didn't hear you say
You were
it.
giving me a weird look as
I thought you said Kepler's or something like that. What?
I see a mosquito in here.
Kepler's laws for
There's a
gravity.
mosquito in here?
Yeah, I just watered them down.
Oh,
Been here for about a
wow,
week.
thank you for that, because I don't approve of mosquitoes.
Now he's not, well, he's
Still
still
not.
here, but
Yeah, well, she probably.
that's true.
Because it's the females that take.
Oh,
the
I don't
lessons.
know that mosquito's pronouns, so.
Well, that's true, maybe.
I am
but-
imposing our ideas on
Yes.
a bug.
Okay,
So-
I believe its pronoun is or something along those lines. All right, so let's present. So Mark, I'm gonna stop the video here, and you're just gonna watch this on the what's it called, the presentation, and then you're gonna come back afterwards. What?
Let's make fun of Mark while we can't see.
Oh, we would never do that because Mark is awesome.
Did that get recorded?
No, sadly it did not.
Okay.
But you can say it again.
That's okay.
Okay. I'll spend 5 minutes trying to get this out of this mode. Yeah, okay. First, I'll get the thing back up again. All right, welcome back, Mark. I'm sure you've watched the galaxies and Milky Way videos, and now let's keep on going here. Let's present. So, this is a lovely photograph, which looks better if I turn the lights off. So this is by actually an amateur astronomer. He did this back in 2000. He's made a more detailed one now, but that one doesn't come in this nice convenient size here. Axel Mellinger, who went around the world taking photographs, and then he stitched them together. I think it was with Photoshop. I think there was Photoshop in 2000. But he stitched them together one way or another. So this is the entire celestial sphere in one of those projections where you put it onto like this ellipsy looking thing. I think that's called like ATOF projection or something like that. Do you know, Mallory? Yeah, but does anybody else know? But in any case, he did it so that the galactic plane is the equator of the projection. And these are the two Magellanic Clouds. And there's other goodies here as well. So for example, this is the Andromeda Galaxy right here. And in higher resolution, you can do fun things like, oh, there's Orion and stuff like that. I don't think I can see it in this particular resolution here. But anyway, notice that you can actually pretty much see the disk of our galaxy in this picture. Note too, though, that it's a 360-degree view. In other words, this point and this point are the same as one another. So it's a total wraparound view, projecting the entire celestial sphere onto this ellipsy-looking thing here. And so one thing to understand is that that's what we're seeing when we look at the Milky Way in the sky. We're seeing the fact that we live in the disk of our Milky Way galaxy. We live in a disk galaxy that has stars, gas, and dust concentrated in the disk, but it also has what we call a halo, a spherical distribution of stars, not gas and dust, but of stars above and below the disk. We ourselves live in the disk, and so when we look out into the night sky, when we view in the plane of our galaxy, we see what we call the Milky Way visually, that milky band that stretches across the sky as essentially a great circle on the celestial sphere. And if you look above and below the plane, you don't see that, but you still see stars because we live inside the disk, and so we see stars within the disk, both above us and below us, so to speak. And so we're able to see stars in every direction. And that's kind of, the night sky in a nutshell. Now, William and Caroline Herschel, brother and sister team, back in the 1780s, attempted to map the structure of the galaxy. And Phil Plait in the video talked about what they did without naming them. They did star counting. So in other words, they figured, okay, let's count how many stars we see with our telescopes in every direction. And they made the simplifying assumption, because it wasn't known at the time how bright stars were, they just assumed that they're all the same brightness. They have the same intrinsic luminosity. So then the inverse square law would dictate how bright they appeared to be. And so they assumed that the more stars that they could see in a given direction, the thicker the galaxy was in that direction. If there's more stars, you could see further. If the galaxy's thicker in that direction, you could see more stars in that direction. And so they literally, this is the map of the the Milky Way galaxy that they created based on their star count method. And they deduced that the sun was near the center, and that doesn't look anything like the galaxy actually does. So what do you think it is that was causing them to think that the sun is near the center, and furthermore, that it doesn't actually stretch nearly as far in their map as it does in reality? What are they not accounting for? Dust. Yes, dust. You cannot see very far in the disk of the galaxy because of the presence of dust. And so as a result of that, you can get the impression, if you just count stars, that you live near the center because you can see about the same distance in every direction. And so it looks like you're in the center when actually all you are is in the center of your local region of the Milky Way galaxy as far as you can see due to the dust in it. And so this was very deceptive. It's a good idea, as Phil Plait said, but it wasn't going to work because of the fact that there was all that absorption by dust that they weren't aware of back in the 1780s. So this is, and unfortunately it doesn't really work that well in my opinion, but this is a video of a globular cluster that was made by Nadine Amlacher, an astronomer who was in Switzerland, Federation Helvetica, right, CH there, and that's Switzerland, right, CH, yeah. So anyway, it shows some Cepheid variable stars that are marked with some of these apertures for doing differential photometry, basically. And the RR Lyrae variables, you may remember, are approximately solar mass stars that are at the base of the instability strip in the HR diagram. And they all have about the same luminosity. And so that means they can be used as standard candles. In other words, we know how bright they are. They're low mass horizontal branch stars. They all have about the same luminosity. And so they're a very standard technique because they're quite abundant in globular clusters to determine the distance to a globular cluster. You observe the RR Lyrae variables in it, measure their apparent brightnesses, and then from their intrinsic luminosities, you calculate how far away the globular cluster is. And here's a plot that shows this idea. So here's the period luminosity relation. So Cepheid variables have a wide range of luminosities and periods. RR Lyrae variables are all about 100 times the sun's luminosity, and they all have roughly the same period. So because of that, they make good distance determiners, distance indicators. And Harlow-Shapley used observations of globular clusters and the Cepheid variables within them in order to measure the size of our galaxy, estimate the size of our galaxy. And his technique had the advantage that you don't have to worry about the dust, because the idea is our galaxy is disc-shaped, but it has a halo of stars above and below the disk that is pretty much spherically distributed, and the globular clusters are in the halo above and below the disk. And so that means that when we look at globular clusters, we're looking out of the plane of the disk of our galaxy, not through so much dust. And so as a result, we can see them to much greater distances than we can when we try to look at stars within the disk of our galaxy. And here's a fun analogy from Kaufman and Friedman's Universe book, where I love the fact that they use apparently it's a car from Cuba, or at least it's a 1950s, car. And the idea is, imagine that you are, there's a fog at ground level representing the dust in the disk of our galaxy. You can't see the base of this radio tower because of the fog, but you can see the beacon at the top of the radio tower because when you look towards the beacon, you're not looking through so much of the fog. Similarly, we can see globular clusters to great distances, much further than we can in the disk of our galaxy. So here's Harlow-Shapley's technique. Look for globular clusters up above and below the plane of the galaxy. You can see them well past the distance to the center of the Milky Way galaxy, whereas it's very difficult to see stars in the center of the Milky Way galaxy through all that gas and dust. There's a couple of so-called holes where we can see right through almost to the center, but those are few and far between. And here is a modern plot of distances to various globular clusters. And we can see that the globular clusters form a spherical distribution that is pretty much spherically symmetric around a point, which we infer to be the location of the galactic center. And based on these observations, the sun is about 8 kiloparsecs, about 25 or so thousand light years, from the center of the distribution of globular clusters, and that's how we know how far we are from the galactic center. That's how far we know, that's how we've located where the galactic center is, basically, is looking for the distribution, center of the distribution of globular clusters. So Harlow Shapley was the first person to do that. So, then meanwhile, here's a nice kind of artist's rendition of the structure of our galaxy. So you can see galactic disk, there's the galactic bulge consisting of very old stars at the center, and so it's reddish as a result because there's no active star formation, or at least not much in there anymore, so the O and B type stars died long ago, and the most luminous stars there would then be relatively low mass red giants. And so it gives it an orangish, reddish, yellowish kind of appearance. Whereas the galactic disk contains the spiral arms with H2 regions and sites of active star formation. And so it contains O and B type stars, not many as a fraction of the total population, but the most luminous O and B type stars are tens of thousands, even hundreds of thousands of times more luminous than the sun. So as a result, they actually dominate the light of the galaxy in visible light, even though they're only a tiny fraction of the population. And so when you look at a color photograph of a spiral galaxy, it tends to look bluish in the spiral arms, but the bulge looks kind of reddish in color because of the very different populations of the most luminous stars in the two locations. And then you can see represented there the galactic halo. There's lots and lots of so-called field stars in the halo, and then there's also globular clusters. Some of the stars are located in the so-called globular clusters, spherical distributions of stars. The globular clusters, as we'll see down the road, are, for the most part, all very old, billions of years old, much younger than open clusters are. Open clusters are the kind of things that are forming in H2 regions now within the disk of the galaxy. Any questions? So here's another representation of our galaxy structure. So there is, but careful star counts show that there's both and this is, I know it's very cartoonish to say the least, but there's a thick disk of older stars and a thin disk of younger stars. So there are two populations of stars within the disk. They have different scale heights, different characteristic distances over which their densities fall. We can identify two populations, the thick disk and the thin disk. The thin disk tends to contain younger stars, and then again the halo, the bulge, and globular clusters. Yes, very cartoonish representation of the structure of the Milky Way. Here's another representation of the structure of the Milky Way, kind of an up-to-date view, not in detail. In other words, there's artistic license in terms of where particular H2 regions and all that are shown, dust clouds and all that. But in other words, various techniques have indicated that our galaxies are barred spirals. So you can see that the bulge is actually not spherical in the center. It's a nearly cylindrical structure of old stars. And there are 4 spiral arms, 2 major ones, 2 minor ones, and the sun right now appears to be on a little fragment of a spiral arm called the Orion spur. So remember that we have right ascension and declination for mapping coordinates on the sky. And there's also an alternative system if you're studying the Milky Way called galactic coordinates, which uses the plane of the galaxy as its equator. And then for galactic longitude, that is angle, that's the angle L there in the figure, it's angle away from the galactic center towards the east on the sky, along the plane of the galaxy, so along the band of the Milky Way in the sky. You have to arbitrarily define a great circle to be the galactic plane because the galaxy has some thickness. And then the points that are 90 degrees away from the great circle of the galactic plane on the sky, the intersection of the galactic plane with the celestial sphere, that's the NGP and the SGP, the North Galactic Pole and the South Galactic Pole. And galactic latitude is that angle B indicated in the figure there. So angle away, north or south of the galactic plane, the galactic equator. And so we specified galactic coordinates with L and B, those two angles, L and B. Here's a fancy schmancy, I know, a fancy schmancy. What's that? As you can see here, right, but it's actually not quite as complicated as it looks. If you look very carefully, then you can see the logic to it. We usually, most astronomers use right ascension and declination based on the celestial equator, the projection of the plane of Earth's orbit onto the celestial sphere, and then there's the north celestial pole and the south celestial pole, and then they've also drawn ecliptic coordinates, where you've got the north ecliptic pole, the south ecliptic pole. In ecliptic coordinates, it's the, I'm sorry, I misspoke. The celestial equator is the projection of Earth's equator onto the celestial sphere. Earth's equator, I was thinking of the ecliptic coordinates. With ecliptic coordinates, that's where you project the ecliptic, the plane of Earth's orbit, onto the celestial sphere. And then its poles are the north ecliptic pole and the south ecliptic pole. And then with the galactic coordinates, the ecliptic is tilted by 62.6 degrees relative to the galactic equator. So in fact, our orbit around the sun is rather skewed to the plane of the galaxy. Our orbit is tipped by almost 63 degrees relative to the plane of the galaxy. We are not orbiting parallel to the plane of the galaxy. We're orbiting at a pretty steep angle to the plane of our galaxy. So, spiral galaxy M83, seen in visible light. We've seen this one before, along with when we were talking about star formation. This 21 centimeters wavelength radio image that indicates that the H1 clouds are concentrated along spiral arms. So we've met this picture before. And we talked about how it's spin flip radiation. And those are the key 21 centimeter observations to allow, those are what allowed us to map the spiral structure of our galaxy. So the idea is that, first of all, the wavelength's very long, so they don't care about dust. You can see straight through the galaxy at 21 centimeters wavelength. You don't have to worry about dust clouds. The galaxy is rotating around the galactic center. And here's the sun's location. And you imagine, let's point our radio telescope along a certain line of sight in the disk of our galaxy. There will be H1 clouds at various distances from us along that line of sight. And the idea is that the different H1 clouds will exhibit different Doppler shifts because of there being different motion of those clouds relative to us due to the galactic rotation. So in other words, here's a point for a cloud which is at R min. In other words, along this line of sight, it's as close as you can get along that line of sight to the galactic center. Here's another one nearby to us. The one nearby to us is shown right here. It's got a small Doppler shift. It's positive, so the idea is it's moving away from us. It's got a red shift. It's relatively small. So first of all, why should it be a red shift and why should it be moving away from us? Well, the idea is that closer in, it's closer to the center, so it's moving a little bit faster. As we'll see, the rotation curves are actually nearly flat, but also it's not very far from us, so it's not going to show a very large Doppler shift as a result of that. However, over here on the far side of the galaxy, if you put in how we're moving and how they're moving, our distance is actually diminishing from that, I guess. I have to think about it here. I had it in my head before. But anyway, the big picture is that because of the rotation of the galaxy, then everything's going around this way. That's right. So it's diminishing because we're catching up to it, so to speak. As we go around the bend, we're catching up to it. So its distance is diminishing. So it shows a blue shift as a result of that. So the details are in the book, and it's pretty tedious, and I'm not going to go through it here. But the idea is that if you have a model of the rotation curve of the galaxy, then you can deduce where the different clouds are along the line of sight from their Doppler shifts. And if you do that along various lines of sight, use the Doppler shifts to disentangle their distances from us, then that's how you produce a map like this, where of how the H1 is distributed in our galaxy, 21 centimeter radiation from our galaxy. So that's how we're able to tell from the inside that there is a spiral pattern to the galaxy. Because we see in other galaxies that H1 clouds tend to be concentrated along the spiral arms. This is Lord Rosse's 6-foot telescope named Leviathan. So this is from back in 1845. It's not 6 feet tall. 6 feet is the diameter of the objective. Yes, right. It's much, much taller than 6 feet. And so he was a lord, so he was wealthy, and he was a very enthusiastic amateur astronomer. And so his hobby, as it were, was building really, really big telescopes so that he could try to see things as best he could. Yeah, I'd like to be able to have a hobby like that. This is a restoration. It fell apart and then it was restored. So imagine, a complicated contraption for pointing that thing. Here is his sketch of the galaxy M51. So with his telescope, he was able to visually see some spiral structure in M51. And so that was the reference to the idea that there were spiral nebulae. Some nebulae, they didn't realize they were necessarily external galaxies, but they had a peculiar spiral structure to them. The philosopher Immanuel Kant hypothesized that they were island universes, that they were other Milky Ways, essentially. And he didn't have any hard evidence for that, but he got it right. He got right the idea that the spiral nebulae were in fact separate islands of stars from our own Milky Way. That we do not live in the galaxy, that we live in a galaxy. Here's a Hubble Space Telescope photograph of that same galaxy, M51, where you can very clearly see the spiral structure. Yeah, I don't know if they have the same orientation. Yeah, they're pretty close to the same orientation. Yeah, so.
Yeah, even the clunk of the cover edge.
You're talking about the big thing on the right there? Yeah, that's actually another galaxy that's interacting with it.
Yeah, I'm just like, it's the same orientation.
Yeah, right. So that tells us that, yeah, these are essentially in the same orientation. Yeah, and in fact, you can even see, like this H2 region here appears to be visible in Lord Rosse's drawing here. Yeah, pretty cool, huh? So, visually, you couldn't tell that the spiral nebulae were made of stars. You couldn't see the H2 regions and so forth very clearly. You need long exposure photographs. In the early 20th century, the photography still wasn't good enough to resolve them into stars. And so there was this big debate between Harlow Shapley and Heber Curtis. They called it the debate, but it's neither side had enough evidence to definitively determine the answer to the question, are the spiral nebulae other Milky Ways, other galaxies, or do we live in the galaxy? Harlow Shapley, this was in 1920, I think it was, Harlow Shapley favored the idea that we live in the galaxy, that the spiral nebulae are just nebulae within the Milky Way. And it was thought then that the universe had a system of stars in it. Heber D. Curtis championed the idea that they were external galaxies, that there was not just a galaxy, but there were many galaxies. That we were not living in the galaxy, that there were many galaxies. I've never seen it presented this way, but it seems to me that there would be a psychological reason for Harlow Shapley wanting there to be just one galaxy. And that is Remember, he's the person who used the globular clusters to determine the distance to the center of the galaxy, and thus to measure the size of our galaxy. If it is the galaxy, then you've essentially measured the size of the universe, as it were. If it's a galaxy, you've measured the size of one galaxy, the one we happen to live in. So it seems to me, maybe even subconsciously, he wanted there to only be one galaxy because then his achievement is maybe a little bit more magnificent than if he just measured how big our particular galaxy is. The debate was resolved by this guy. Perhaps you've heard of him before. Never, huh? Right. Edwin Hubble, who among other things had been a high school wrestling coach, it turns out. He was quite a guy. There's this photograph where his wrestlers, signed it and said what a great guy he was and stuff like that. Apparently he had quite, he thought highly of himself, apparently. I mean, look at the pose, right? Here I'm puffing my pipe and all this. But in any
Had
case.
pictures with that pipe.
What's that?
Like almost all his pictures are.
Have that pipe, that's right, yes, it was kind of characteristic of him there. Although I guess they discourage smoking a pipe while you're sitting in the cage of the telescope next to the optics there. So there he is, sitting in, I believe that's like a cage in the 100-inch telescope that he used. I think this is the one that he used to make his observations of the Andromeda Galaxy, where this is a very famous photograph because he has marked several locations where there are novae, right? So we talked about novae, where you have a thermonuclear eruption on the surface of a white dwarf because it gets hot enough and dense enough for the layer of hydrogen that accumulates to erupt into hydrogen fusion. So you look at something with more than 100 billion stars in it, and you're going to find some novae. Here's one that says novae too, but then he crossed it out and wrote VAR! Exclamation point. And that's because he realized upon making further observations that it was in fact a Cepheid variable. So its brightness was varying with time, and it had the light characteristic of a Cepheid. So he could measure the period. It was, I think it's 31.415 days there. And he could use the period luminosity relation and determine the distance to the galaxy. He got a wrong answer, but, so he got 900,000 light years. Now we know it's more like 2.5 million light years. But that's okay, because even his wrong answer was good enough to say, this is not in our galaxy, because even, as Phil Plait mentioned, even the largest estimates of the size of the Milky Way were much less than 900,000 light years. So, boom, that clinched it. He had determined definitively that the Andromeda Galaxy was, in fact, a galaxy, a separate city of stars from the Milky Way.
So that dude's discovery of the size of the Milky Way was his ultimate downfall.
So to speak, right? Yeah, so to speak. But I mean, the thing is it's okay to be wrong, right? No, it's not, huh? Right. Good luck with that as a life philosophy. I'll stick with it's okay to be wrong, and of course, Harlow Shapley well deserves his fame for being the first person to determine how big our galaxy is. Right? That's no small accomplishment right there. So we'll leave it here for now.
Bye, Mark.
Bye, Mark.